Great. So let's talk about timers again. So I did talk a little bit about timer 0, which I will repeat in the first couple of slides, but then we'll go forward with timer 2 and then timer 1. So what did we talk about? So this is the layout of what's going on in this hardware device called timer 0. And we see here this counter, TCNT0, that is being incremented according to a clock that is pre-scaled, and which is what you will be programming. So for example, the CPU may run at 60 megahertz, and if you pre-scale it with a factor, say, 64 or something like that, then you would get a much smaller clock that will clock through this particular increments on this counter. Now, if it's equal to this register, you may have programmed this hardware timer of yours in a way that it, for example, generates a certain waveform over this channel, channel A, or in addition, you may add some kind of interrupt service routine that will be called when a match happens. And the same for channel B and a match with this particular register OCR0B. Then you got two control registers that we talked about, the TCCR0A and the TCCR0B. And with those you will set your prescaler and a couple of other things, including what you would like to have for interrupts, like when you would have an interrupt, for example, for when this counter is actually overflowing and goes beyond its 8-bit representation, so it effectively circles back after 255, goes back to 0, and that may also create a hardware event. So this is the general picture, and we talked about this somewhat simplified picture where we see that you have a divider which is given essentially by these three coordinates, these three positions in this particular register, the TCCR0B. We have 3 bits that you set in a certain way so that this mux will select a certain divider, say division by 1, so no scaling, no pre-scaling, or division by 8, and so on. Now, that tells you how fast this is actually incrementing, and this is just a register, it's just an integer really, 8-bit integer that is going to be incremented, and here you have your channels and the comparators. Now, we talked about this particular program, and in which we explained, how do you use timer 0 to, for example, implement a software clock, and this is actually really important in our task-based programming approach. So let's see what we want. Well, in the end, what we really want is something like this, a while loop that says, if a condition is satisfied, like 1 millisecond has passed, that's what I would like this to represent, then call this task, and after that I reset this software task timer to a initial value, so that when it decrements over time back to 0, again 1 millisecond has passed. But that means that you will only execute this code when this condition is met. And that means that you can extend this while loop with a whole bunch of other code that could be called while this software task timer is decrementing back to 0 in that 1 millisecond. And that means that in that 1 millisecond you can do a lot of other stuff. Now the general layout is some initializations. You may have an initialization timer 0, maybe an initialization of your LCD screen. Other stuff, some pins are input, some pins are output, you all put it in here, and then you enable the global interrupts, right? And after that you start to get into this infinite loop, so you never get out of this loop. It's a while one, the main will always continue to work. So your MCU is now a continuously, well, as long as it is powered up, working device. Now, how do we get this timer? How do we get this condition to represent 1 millisecond, that much time has lapsed? Well, what we want is, we want some interrupt service routine based off timer 0 that is going to effectively use the timer 0 as a very reliable hardware clock to to decrement the software task timer. Here we initialize at 500, and so every time this one is called, you decrement 500 by 1, then it becomes 499, 498, until it's 0, and you do not go any further because there's a condition in here that says only when it's larger than 0 you decrement. So it will stop at 0. After that this ISR may be called again and again, doesn't matter. This condition is not true anymore because the software task timer is already equal to 0, so it will not decrement any further. But what you know now is that at least 500 ticks passed during the time that this particular condition was matched last time. So 500 times this was decremented and this interrupt service routine was called. Now, we can now say, for example, let's use a 1 millisecond ISR in this particular example, with which we initialize this timer. So what do we really want? We want that this particular ISR is going to be called every 1 millisecond. So that means that 500 now corresponds to 500 milliseconds, and that would mean that this particular task is called every half a second. For example, toggling the LED, and then you would have a certain visual experience about how fast this LED is being toggled, like every half a second, giving a period of 1 second. Now, how do we initialize this stuff? We will see control registers, that's this one, the TCC R0A, and you create a certain, well, you look into the data sheet, that's always how you would do it. When you want to do this from scratch, of course I talked about it, but the point is that you look in the data sheet, you look at how this TCC R0A is defined, and you will see which positions are readable, which ones are writable, which ones are read and writable, what are their default values, and each position is indicated by some name, for example WGM01, and that means that that position, which is just some constant, right, indicates a certain functionality. So you really program that particular hardware device of yours. In this particular case, you say, I want to do a clear on compared with A. So that means that if the TCNT0 is equal to your OCR0A, when they're equal, then the TCNT0 goes back and is cleared back to 0 and starts counting again upward. Now, here we say that it should be cleared at 124. So OCR0A sets the number of ticks. Now remember that this corresponds to a period of 125. Why? Because from 124 you go down to 0, to 1, to 2, 3, 4, to 124, and if you look at the number of transitions, there's actually 124 plus 1 is 125. Now, you enable here the timer 0 compare A. So when this register 124 matches your counter TCNT0, then if you set this particular register to 2, it means that the second bit, right, in the register is equal to 1, because that's the binary representation of the integer 2, and that corresponds in this mask that you are enabling the ISR that compares, that corresponds to that matching. So whenever this register matches the TCNT0, a hardware interrupt is going, or like a hardware event is generated, that will be caught by your interrupt